Right now, you are made of water. Not mostly water, not kind of water. About 60% of your body is water. Your blood is water. Your brain is water. The fluid cushioning your spine is water. You are, in a very real sense, a bag of ancient ocean carrying itself around on two legs. And here is the part nobody ever tells you. That water inside you right now is old. Not old like last week. Not old like ancient Rome. Old like 4.5 billion years old. The water you drank this morning has been on this planet longer than the continents you are standing on. And here is the part that should stop you completely. Scientists are not entirely sure where it came from. Most people assume Earth always had water, that it was just here from the beginning. That is not quite right. And the real answer involves something so violent and so ancient that it rewrites everything you thought you knew about the ground beneath your feet. Stay till the end, because the last part of this video will change how you think about every glass of water you ever drink for the rest of your life. Here is where we need to start. 4.5 billion years ago, there was no Earth. There was just the sun and a spinning disk of gas and rock and dust surrounding it. Imagine standing inside that disk. Not that you could survive it for a millisecond, but imagine it. Chunks of rock and metal slamming into each other at tens of thousands of miles per hour, fusing, growing, merging into larger and larger bodies. This process is called accretion, and it is violent in a way the word violent cannot properly contain. The young Earth was not a blue-green planet. It was a hellscape, a ball of molten rock covered in oceans of liquid magma. Surface temperatures hot enough to vaporize metal. No atmosphere, no liquid water, no anything resembling the world you know. So here is the first question. How does a ball of molten rock become a blue planet covered in liquid water? The answer comes in two parts, and both of them involve things falling from space. Part 1. Comets. Comets are essentially dirty snowballs drifting through the solar system. They are made of ice, dust, rock, and complex organic molecules. When they pass close to the sun, the heat vaporizes their surface, creating the long glowing tail that makes them visible from Earth. For decades, comets were considered the most likely source of Earth's water. The logic made sense. Comets are full of ice. Earth was hot. Comets crashed into Earth. Ice melted. Water. It is a simple, elegant story, and it turns out to be only partially right. Here is the problem. Not all water is the same. Water is H2O, two hydrogen atoms bonded to one oxygen atom. But hydrogen comes in different versions. Regular hydrogen and something called deuterium, also called heavy hydrogen. Deuterium is identical to regular hydrogen, except it has an extra neutron in its nucleus. That extra neutron makes the water molecule heavier, and different sources of water have different ratios of regular hydrogen to deuterium. Scientists call this the D/H ratio, the deuterium to hydrogen ratio. It works like a fingerprint. Every source of water in the solar system has its own D/H fingerprint. And when scientists measured the D/H ratio of comets and compared it to the D/H ratio of Earth's oceans, they did not match. Comet water and Earth's ocean water are chemically different. Not completely different, but different enough to matter. Specifically, the comets that were first analyzed, the Halley type and Oort cloud comets, had about twice the deuterium concentration of Earth's ocean, which means if comets were Earth's only water source, the oceans would be a fundamentally different substance than they are. So where is the rest of the answer? Here is where it gets genuinely wild. Part 2. Asteroids. Specifically, a type of asteroid called carbonaceous chondrite. These are among the most primitive objects in the solar system. They formed in the earliest days of the solar system, before the planets existed, and they are saturated with hydrated mineral, rock that is chemically bonded with water molecules during their formation. When a carbonaceous chondrite hits a planet, it does not deliver liquid water. It delivers water locked inside the rock itself. Heat from the impact releases that water. And here is the critical thing. When scientists measured the D/H ratio of carbonaceous chondrites, it matched Earth's oceans almost exactly. That match was a landmark discovery. It suggested that Earth's water, or at least a very large proportion of it, was delivered by asteroid bombardment early in the solar system's history. Not by comet, by rock, dirty rock that crossed the solar system and slammed into the young Earth over and over and over for hundreds of millions of years. And here is where the story gets even stranger. Because for a long time, scientists thought the answer was simple. Asteroids delivered the water. Problem solved. But then Then researchers started looking more carefully at specific comets, particularly a comet called 67P/Churyumov-Gerasimenko. In 2014, the European Space Agency's Rosetta mission reached this comet after a 10-year journey across the solar system. Rosetta was the first mission to orbit a comet, and one of its key jobs was to measure the comet's D/H ratio. The result was surprising. 67P had a D/H ratio 3 times higher than Earth's ocean, even higher than the Oort cloud comets measured earlier. That seemed to close the door on comets as a water source even further. But then in 2019, scientists analyzed a different type of comet, a comet called 46P/Wirtanen. This one is what astronomers call a hyperactive comet. It releases much more water than normal comets of its size, and its D/H ratio was very close to Earth's ocean. Suddenly, the comet door was open again. Scientists realized they might have been measuring a biased sample. Most of the comets we have analyzed come from the outer solar system, the Oort cloud, but many early comets may have come from the Jupiter family, closer in, with different composition, and those comets may have D/H ratios much closer to Earth's water. So right now, the honest scientific position is this: Earth's water probably came from multiple sources, a large fraction from carbonaceous chondrite asteroids, a possible significant fraction from comets of the right type, and potentially some water that was already present in the dust and rock that formed the Earth itself. That third possibility is newer and more controversial, but some researchers now believe that even the hot, violent early Earth may have retained some of its original water, locked in minerals deep inside the planet, and over billions of years, gradually released through volcanic activity. Let's think about what that means. When a volcano erupts, it does not just release lava, it releases gases, carbon dioxide, sulfur dioxide, and water vapor. Enormous amounts of water vapor. Over hundreds of millions of years, volcanic activity may have outgassed significant quantities of water from Earth's interior to its surface. This is called volcanic outgassing, and the water it produces has its own D/H fingerprint, one that in many samples is close to Earth's ocean water. So we now have 3 competing candidates for the origin of Earth's water: asteroids, comets, and the planet itself. And the scientific consensus right now is that it was probably all 3, in different proportions, in different eras, over hundreds of millions of years. Earth did not receive its water in one delivery. It accumulated its water in stages, a cosmic layaway plan that unfolded over geologic timescales. But here's where the story takes a turn that nobody sees coming. Because even if we accept that asteroids and comets delivered most of Earth's water, that raises an even deeper question. Where did the water in the asteroids and comets come from? You might think that is where the trail ends. Space, fine, but it does not end there. Water, H2O, is one of the most common molecules in the universe. It forms spontaneously when hydrogen and oxygen atoms meet under the right conditions. Hydrogen is the most abundant element in the universe, created in the Big Bang. Oxygen is produced inside stars through nuclear fusion. When stars die, when they explode in supernovae, they scatter oxygen into surrounding space. That oxygen combines with hydrogen, and you get water. In molecular clouds, in the gas and dust between stars, water forms everywhere. The ice on the asteroids and comets that delivered water to Earth was not created here in our solar system. Some of it was created in interstellar space, in clouds of gas and dust that existed before our sun was born. When our solar system formed, it collapsed from one of those clouds. That cloud contained ice, and that ice became part of the asteroids and comets. And some of that ice eventually hit the Earth and became the oceans, and became the river, and became the rain that falls on your roof, and became you. Let that land for a moment. The water in your body contains hydrogen atoms that were created in the Big Bang 13.8 billion years ago. The oxygen those hydrogen atoms are bonded to was created inside a star that died before our sun was born. That star exploded. Its oxygen scattered into space, mixed with hydrogen in a molecular cloud. That cloud collapsed to form our solar system. Some of that oxygen and hydrogen bonded into ice on asteroids and comets. Some of those asteroids and comets hit the early Earth. The ice melted into ocean. The oceans evaporated into clouds. The clouds became rain. The rain filled rivers and aquifers. And somewhere in that chain, over billions of years of cycling, some of those ancient water molecules ended up inside your cells right now. You are not just looking at the universe from the outside. You are built from it. And here here's the question that follows from all of this. If Earth got its water from space, and water is common throughout the universe, does that mean other planets could have water too? The answer is yes, and it is not hypothetical. Mars has ice at its poles right now. Ancient riverbeds and valley net cover its surface, evidence that liquid water once flowed there billions of years ago. Europa, one of Jupiter's moons, has a vast liquid water ocean beneath its frozen surface, a deeper ocean than any ocean on Earth. Enceladus, a moon of Saturn, is actively venting water vapor into space from cracks in its icy shell. The Cassini spacecraft flew through those plumes and detected water, organic molecules, and hydrogen, all the ingredients for life as we know it. Water is not rare in the universe. It is everywhere, on moons and dwarf planets and comets and asteroids, in molecular clouds between the stars, locked in the minerals of rock across the solar system. And this means something profound about the search for life beyond Earth, because every time scientists find water somewhere in the universe, they find a place where the story of Earth might be starting over. A new planet, new chemistry, new billions of years, maybe new life. And this brings us to the thing nobody says clearly enough. The fact that Earth has liquid water on its surface right now is extraordinary. Not common, extraordinary. Earth sits in what astronomers call the habitable zone, the Goldilocks region around a star, where a planet is not too hot and not too cold for liquid water to exist on its surface. Not just ice, not just vapor, but liquid water. That is the narrow sweet spot that allows ocean. And oceans are where life, as far as we know, begins. And here is the final layer of this story. Because even after we understand how water got here, after we understand the asteroids and the comets and the volcanic outgassing, after we understand the D/H ratio and the molecular cloud and the supernovae, there is still a question that does not have a full answer. Why did the water stay? Mars had water once, it lost it. Venus had water once, it lost it. Earth kept it. Earth kept it because of its magnetic field, which deflects the solar wind that would strip the atmosphere. Earth kept it because of its mass, which creates enough gravity to hold an atmosphere. Earth kept it because of a moon that stabilizes its axial tilt, which stabilizes its climate. Earth kept it because of the right distance from a star of the right size, the right geology, the right chemistry, the right everything. The chain of coincidences required for liquid water to persist on a planet's surface for 4.5 billion years is staggering. One link breaks, no water, no life, no you. And here is the gut punch. You take a drink of water today without thinking about it. You run water over your hands without considering where it has been. But that water has traveled further than any human explorer in history. It was born in the death of a star that lived and died before our sun existed. It crossed the solar system on a piece of rock. It survived the apocalyptic early Earth. It evaporated and rained and evaporated and rained for billions of years. And eventually, after all of that, it ended up here, in a cup you hold in your hand, in the cells of your body, in the tears you cry, and the blood in your vein, and the fluid between your neurons as you process this thought. You did not come from Earth. Earth came from space, and so did you. Every single atom of you was somewhere else before it was here, and every glass of water you ever drink is the universe reminding itself that it is still alive.